All right, so section 8.1 and 8.2, we're going to start moving into relations on sets. Like we didn't talk a ton about sets yet. That's true. Really, this whole book can be done a little bit here, a little bit there. That's kind of how I like to do it. I'm teaching the stuff obviously has to be taught. I guess in the order in which I think it's the most important-ish, I guess. Whatever. So anyway, section 8.1 and 8.2, all of chapter 8 is all about relations. And so it's not very hard. It's just a little odd sometimes the way they write it out. So a couple things I want to review, and probably you're fairly comfortable with it. Those of you especially who've done any programming at all. Modulo or modular arithmetic. And so we'll talk about it a little bit more later on too. We'll use it quite a bit going forward. So just a little background here, because one of the things that they'll do in this is they'll randomly bring up modular arithmetic as if everyone studied every chapter in this book, even though technically that's not something that we're supposed to cover exactly. All right, it shows up, but it's not like it's, something that we talk a ton about. So modular arithmetic is the idea, for instance, on a clock. Currently it is 10 o'clock where I'm at right now today, or dang near 10 o'clock, I guess. If you're cheating looking at my thing down here, it's not quite 10, but we're going to pretend. Right? So what time will it be in 3 hours? Well, anyway, the brain knows it's 1 o'clock. But anyway, the brain goes, no, that's not right. It's 13 o'clock. And so the idea here is that we deal with what we have on our clock is what we call mod 12. Mod 12. So the idea is 10 plus 3 is 13. And 13, we say, is congruent to 1 in mod 12. And the reason for that is because 13 divided by 12 is equal to 1. Don't care about that. Remainder 1. Okay? This one we don't care about because that means we went around the clock an entire one full time around. Don't care. We ended up right here. It's very similar to on The Price is Right back in the day when I was a kid. Watched that sometimes with my grandmas. And both of them just love that show. And I always wanted to go on there and spin the wheel backwards, freak old Bob Barker out. Okay? You see a Marine get on there from Camp Lejeune, Camp Pendleton, wherever, and he'd spin that wheel he'd go around 87 times. Didn't really matter because it ends up where it lands is what's important. Or you get the old gal on there, Bob has to help her spin the wheel, and it just barely gets around one time. All it matters is it had to go around once. It doesn't even matter which direction it went around the circle, okay? Because what it matters is where it lands. So if you get something that was mod 5 arithmetic, think about this. The only numbers you can get are 0, 1, 2, 3, 4, 5, because those are the only only remainders you can get when you divide by 5. Okay, so check this out. 37, well, what does that equal to? I don't know. So we say, what is it congruent to? That's what, hence the 3 numbers there. 37 divided by 5 goes in 7 times with a remainder of 2. So we say it's congruent to 2 mod 5. Okay? You're like, well, okay, well, it's not that hard. No, it's not. 107 is congruent to mod 3. Sure. Now remember, the only numbers you can see on a mod 3 clock are 0, 1, and 2. Okay? So if I look at this, they're the only possible remainders I can get. Well, how many times does 3 go into 107? I don't know. 3 goes in 3 times. Oops, that's a 9. Sorry, remainder 1, 17. 3 goes into 17 5 times. Boy, stupid. Learn how to do arithmetic. What are you? Good Lord. You got a degree in math and you can't even do simple. There you go. Remainder 2, yo. Remainder 2. And so it is 2. And that's all it is. Meaning that you're going to go around the clock. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 32, 33, 34, 35. And then there's the 1, and then there's the 2. And that's where I'd end up, right here on the 2. Okay? That's all it means. Okay? Let's see. Well, mod 2, of course, is just another fancy way of basically saying binary, 0 and 1, right? So 0, 1 clock. And so anything that's odd, of course, is going to be mod 1. Anything that's even is going to be mod 2. It's going to be 0. Okay? So 37 is right now 1 mod 2 every single time. Okay? 38, of course, would be goose egg. Right? Notice that you can do addition, whatever, something like this. Can I add it first? Of course you can. That's 52, 68. 68 is equal to blah, mod 4. Okay, well, blah, see, goes in 17 times, the remainder of 0. Bam, done. What? That's right. Could you do it this way, Jay? Could you do 21 is congruent to blah, mod 4? And whatever you get from that, you can add to 31, which is equal to, whatever you get, the answer here is mod 4 plus 16 mod 4. Could you do it this way? Yes, of course you can. Let's see, 16, 4 goes into 16 evenly, so it goes in, there's a 0 remainder. 4 goes into 31 7 times, remainder of 3. 4 goes into 21 5 times, remainder of 1. So 1 plus 3 plus 0 is equal to 4. But what is 4 in mod 4? 0. I don't like to do it this way because it's more work. Okay, I'd rather just get one big answer and then divide it like that. To me, that's the easier way to go. Okay, but you're welcome to do it any number of ways you want. Another one here that kind of comes to mind is, what if I had a negative? I don't know. Just made that up. What is this congruent to in mod? Sure, mod 3. Sure. All right, so got this here. You're going to get negative 63 plus 14 is negative 49, I guess. Is that right? I think so. Blah mod 3. Okay. You're like, well, it's easy, Jay. 3 goes into negative 49, negative 16 times. Yeah, I agree. And it gives you a negative. It gives you a remainder of negative 1, if you will. Okay. Which is weird. So think about that saying to you. Okay. So here's my clock. Okay. So I'm going to go around this clock backwards 16 times. Okay. So I'm going backwards. That's 1, and then 2, and 3, and 4, and 5. And then I'm going to get, when I get back 16 times, I'm going to go negative 1 more. Where does that put me? It puts me here. So when it's a negative, the way I always tell people is, again, we don't care about this, but we got our remainder is negative 1. So what I always do is I take the mod number, right, plus the remainder. Or if you want to think of it as subtract the remainder, whatever you want to think about it as. But anyway, so the mod number was 3, 3 minus 1, because it's a negative remainder. 3 minus 1 gives you what? Oh, it gives you 2. Bam, there's your answer. In other words, you're going 1, but in the negative direction. Okay? So that's our general brief take on modular arithmetic. We'll see it again later when we get to ISBN numbers, when we get to VIN numbers, when we get to UPC codes. All of those use either a mod number, or they fix it so that it has to be 0 in mod whatever. Okay, so in other words, sometimes it comes down to some codes they'll use an actual, whatever the mod there is, that is your check digit. Sometimes the check digit is whatever you have to add to get a 0, mod 10 or whatever. Okay, and so we'll talk more about that later on. We will use modular arithmetic several more times. Now, the way that sets will be denoted in your book will be something like this. I will pull up an example from the text here. They will say things like this. Okay. For instance, here's a dandy. So A is the set of all strings of A's and B's of length 4. So A is the string of what did I say? A's and B's of length 4. Okay? And we're going to define R on A as follows. We're going to define R, that's the relation, on the set A as follows. Okay? And so for all S and T that are elements of A, S R T goes like this. S has the same first two characters as T. Okay, so let me talk about this for a second. So is the set of 4 of A's and B's. So I personally would like to think of this as kind of like if you have 4 kids. So it could be something like this. You could have all A's. You could have a B. Or you could have, oh, this is hard. ABBA. All right. Dancing Queen. Da da da. Only 17. Oh, goodness sakes. B, A. 1, 2, 3, 4. Okay, come on. You can do this, Jay. You can do it. Maybe. Goodness, I'm having a problem today. Goodness. And that should be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I'm missing one. Yeah, nabbit. Oh, you jerk. And this one. There you go. There's all 16 of them. Good Lord. All right, there they are. Okay. Now, the question is that this right here, for instance, this could be our S. You with me? Cool. This could be our T. Oh, that's cool. Interesting. All right. Any two of them can match up. So the question is, the S has the same first two characters as T. Would this work? No, that wouldn't work at all. All right, because this has A and A, this has B and A, and you're like, oh, that's not cool. Wait. This one and this one could work, though. If this one of them was S and that one was T, that would work. You're right. So you could look at this as, if you will, an X, comma, a Y, if you want to think of it from the standpoint of what we've done our whole lives, except this is just our S and this is our T. Okay? Now, would it work to flip that around? It sure would, because it wouldn't matter if you do this one and then this one, because they still follow the rules, right? Now, that brings up something. And again, I'm going to do 8-1 and 8-2 together, because to me it makes the most sense. When I look at this, I think to myself, wait a minute. If you can do them backwards like that, where, for instance, well, you could do, so let's see, let's do it this way. Let's don't use that. If I do X equals Y, the property of equality, the properties of equality is that Y equals X as well, yes? Okay. And so that's called symmetry. Okay. So some of these relationships will have symmetry. That is, you can flip them around. Okay. And we know that equality, the equality measurement, the equality relation has symmetry. Okay. Now, if it was a situation where you said to me, hey, listen, I have X is greater than Y. Well, that does not work to flip that around and go X is less than Y. You with me? It does not, or well, let me flip that around and do Y is greater than X. It doesn't work. That does not have symmetry. Okay. Because obviously greater than function doesn't have symmetry. Only equality does. Okay. Wait, is this a pair that would work? In other words, is it the same as itself, the first two characters? Well, yeah. This is also a relationship that we have with equality, that A equals A or X equals X. We call this reflexive. It is a property of equality that we've known since we were just a little kid, okay? That something is equal to itself. Yeah, how about that? Cool. All right. Could we also do this? Let me see here. No, I don't want that one. This is also true, yes? A, right? But wait a minute now. Check it out. This is the same as that. You with me? And that is the same as this. So what does that tell you about these two? This one and this one then are also the same. Well, we've known that forever. If x equals y and y equals z, then x is equal to z by what we call the transitive property. Okay? Now, that is something in 8.2 that comes up, that is reflexive, symmetry, and transitive. Okay? I think it matters here because it's what we're talking about. We're going to do some here in a minute that won't be true for necessarily. Okay, now, let's actually get around to answering this question. So check this out. What they want to know is this. They'll ask you some questions like this. Is A, B, A, R, A, B, or ABBA? And the answer is yes. Why? Same first two letters. That's it. Don't get hung up on it. Okay? Is B, B, A, B, B, A. No, because this has BB and this has AB. So they're not the same. Okay? It is literally that easy. Okay? Piece of cake. Okay? I don't want people thinking this is terribly difficult, because it's not that terribly difficult. But just be aware about it. Now, interesting. All right, so here's another one here. So let A equal the set 3, 4, and 5. It's just a set of three numbers. That's it. That's all. Okay. And B 4, 5, and 6. All right, cool. And R is less than. R is the less than relationship. Okay. That is, and this is how your book writes it, so I'm going to write it exactly the way it is. For all x and y, that are elements of A cross B, x, r, y is this. X is less than y. Okay? Cool. What do I mean by that? Okay, what this means is this. You're going to take an x from this fella. You're going to take a y from this one. And that's what we mean. We're going to cross these guys together. We're going to form them up. So where this becomes the x and that becomes the y value. Okay? So we're going to take a value out of this guy. Now think about that. There's 3 choices here and there's 3 choices here. The pairings will be 3, 4, 3, 5, and 3, 6. And then 4, 5, or 4, 4 rather. 4, 5, and 4, 6. And 5, 5, 4, 5, 5, and 5, 6. Okay? Now, which of these are true? Well, clearly this one is true, this one's true, this one's true. This one's true, this one's true, and that one is true, right? Those are the only ones where the first term is less than the second term. So what the question is asking us is this. Now, by the way, I don't have to list them all out per se, but I think it's very easy. It's very straightforward to stop and look at it for a second. And which pairs are in R? Okay, well, I just did that. In this case, they did ask us to list them out. Those are the pairs that are in R. Those are the pairs that are in R. Cool. Nice. Ouch. Stupid nose. Just a minute, one moment, please. Okay, and then it also wants us, sorry about that, to list the pairs that are in the inverse function. Okay, the inverse of R. Well, what's the inverse of R? If you remember back when you were a kid, what'd you do? The y and the x switched places. So the pairs that are in that would be 6, 5, 4, 6, 4, 5, 4, 6, 3, 6, 5, or no, 3, I'm sorry, 5, 3, and where did I leave off? Oh, 4, 3. Those would be the pairs that would be in the inverse relationship. Okay? Again, what happens in the inverse function? If you remember back to high school algebra 2 or something, you found the inverse functions. How did you do that? Remember, you switch the x's and the y's. Okay, so this does tie in. Of course, that only determines whether it's a function or not. Okay, but here, for instance, suppose you had this. This is x equals y squared. Y equals x squared. If you were to switch these guys around, think about what you're doing here. Right? And if you flipped them around, you'd end up with this guy and this guy. What does that amount to? Well, it amounts to a reflection across the line y equals x. Okay? And that's the game. And remember, this one here is not a function because, remember, why? Well, because it does not, the inverse doesn't pass the vertical line test. And you may remember somebody told you about the horizontal line test. This guy here, there's two places where I had a y that was equal to, say, 9. Because of that, when I flip them around, I'm going to have 9 be my x value. It's going to have 2 y's, which obviously is not going to work. Okay. Now, remember, for inverses to work, right, you had to have a function, right? For an inverse to be a function, it had to look something like this. It had to be a 1-to-1 function. Had my function looked like this, where x is greater than or equal to 0, when I flip it around, it ends up being this guy. And the inverse, if this was my f of x, my f inverse of x would actually be a function, remember, to be square root of x. The good news is we don't care if they're functions in this particular setting, okay? We are just looking at relationships, and we're taking the inverse of the relation, and that's all there is. We're not going to get all hung up on it. We're not going to get all weird about it. It's not a big deal, okay? Well, here's a fun one. Let's do this one. I like it. Love it. Let's do this one. 18. So A are the numbers 0 to 8. Is the set of numbers 0, 1, 2, 3, 4, 5, 6, 7, 8. Nice. And we're going to define a relation V. So V is the relation on A. Okay. And it is such that for all x and y that are elements of A, the relationship is as follows. xv y is defined thusly. What in the heck does that mean, Jay? I'm glad you asked. So this is the divides operator. And so what it says is 5 divides x squared minus y squared. What do you mean divides? What it means is evenly. Okay, in other words, this difference better be a multiple of 5 for this to happen. Okay? So let's think about that for a minute. Okay? So first of all, for instance, if you took 8 and 8 to be your two numbers, well, that's 0. Is 0 divisible by 5? Sure it is. It goes in 0 times. Matter of fact, all of them would be that way, right? 7 minus 7, so on and so on and so on. Cool. Now, the rest of them is going to get a little funky, okay? So, listing them all out, my land living, that's going to be hard. There's going to be 64 combinations, I guess, isn't there? Yes? 64 combinations of listing them out, and then you have to see if they all work. Oh, it's so gross. I know that if I take this guy and himself, it's going to work. This guy and himself, it's going to work every time. That's easy. But some of the other ones, it's going to get gross. Obviously, 5 minus 0 is going to work, clearly, because it's going to be 25 minus 0. Yay. Any of the ones like, say, 6 squared minus 1 squared, that's going to work because it's going to give you a multiple of 5. Some of those. And of course, 64 minus 2 squared. Of course, those will work. Some of them are going to be easy, some are going to be hard. So on this particular question here, it says this. Where did it go? Oh, no, it lists, draw the directed graphs for each of these numbers. Oh, like, what are the directed graphs? Cool, okay? And so when I do this, I want to know which ones can you match it up with. In other words, who's my x's and who's my y's, okay? One moment. Sorry, I started to map it. So the directed graphs would be simply a matter of going 0, 1, 2, 3, 4, 5, 6, 7, 8, I guess. Yes, so 0, 1, 2, 3, 4, 5, 6, 7, 8. All of them are going to have one of these guys, yes? Every single one of them. Because they can all match up with themselves, just hunky-dory. Right? And like for instance, I'm fairly confident that if I went from 5 to 0, that would work, yes? Would 0 minus 5 also work? Well, it would be 0 minus 25 is negative 25. Does 5 go into negative 25? It sure does. So that would be a bidirectional difference, yes? Like 64 minus 4 would work, and vice versa. This is interesting. You know what this looks like a job for to me? Looks like a little job for Excel. Why, Jay? Because, God help me, I hate doing extra work that I have to do. It just annoys the bejesus out of me. Okay, I'm sorry. It does. And so this, to me, is where I think it would make so much sense just to whip out a spreadsheet real quick. So what I'm going to do is I'm going to put zeros here. Oops. And so on. I'm going to drag it down to 8 just because oh, come back. And then 1. And drag him down. Come back, come back. Oh, what are you doing? 48. 56. I feel like I'm screwing something up, but I guess we'll figure it out here in a second. Oh, it's actually going to be 81. That's right. No, that's not right. No, what are you doing? 8. Did I mess that up? I might have messed it up somewhere. I don't know. Well, we'll find out here in a second. So 72. So there's 8 of those. Is there 8 of those? Yep. There 8 of those. Yep. 8 of those. Yep. I guess that makes sense. 8 times 9 is 72. It just sounds goofy. I don't know. It sounds weird. I don't know. Okay, cool. I guess we're good. So then I'm just going to do 0, 1, 2, 3. Drag down here to 8. Oh, that's the problem, you jerk face. There's your problem, jerk. Darn it. Insert. Down. 0. Crap. That's my problem, friend. All right, I got this now. I got this. Control C. But I do want to say that I have a serious problem doing all this by hand. You with me? Because I have better things to do with my time. Paste. Oh, what an idiot. That should be a 1. Oops, don't do that. Paste. Paste, I said. Damn it. Control C. Paste. Paste. Darn it. Paste. Darn you! I'm just going to do one thing at a time because I'm going to screw this up if I don't. Paste. There should have been 9 of each of those, and I'm stupid and didn't do that, so sorry. We'll get there. I promise. All right, so let's go grab these dudes. Control X, Control V. I think I'm missing one. Yep. All right, back up, back up, back up, back up. I don't know, drag it down, I guess. About 100 ways to do this. I'll just grab the 6s, dummy, it's easier. Oh, darn it. Got it. All right. Where the darn 4's at? Oh. Yay, we watched Jay play with Excel today. It was so fun. Okay, there they are. Finally. Good Lord. All right, so that's what we're going to do. Is what we going to do. So equals. This guy square minus this guy square. Done. Boom. Paste. Go. Cool. Now, what you can do is you can go through and obviously pick off the ones that work. That's cool. Another fancy way to do this is to go mod. Oh, baby. This number, comma, 5. And what we're looking for is a 0. Anytime you get a 0, that means it went in evenly. Nice. So, of course, 5, 0. Cool. As promised, 1, 1 works. As promised, 4, 1 works, because that's 16 minus 1 is 15, and so on, and so on, and so on. And you could list them out this way. I think that's a slick way to do it. It makes sense. I think it makes your life a little easier. Okay, then you just come in here and go, oh yeah, cool, 4, 1. Boom, done. And then does 1, 4 work? I don't know. Let's find out. So we already know it did, because up here I did 4 and 1. 4 and 1 worked, obviously. And up here somewhere you saw that 1 and 4 also worked, correct? So, of course, that would be a bidirectional arrow. Where's 4 and 1? Oh, I do it to 4 and 2, dumbass. 4 and 2. So 4 and 1, and there you go. Yay! Cool, right? So you can be drawing some of those graphs out. Okay, not very hard, and I encourage you to use Excel to speed the process up, if need be. I mean, it's 81. You're not going to go through and do them all by hand. That's ludicrous, and I don't want you to do that. Okay? That is, if you will, the essence of what we're doing in chapter 8.1. I'm going to do one more example here, and then we'll move on to 8.2 exactly. Now, I have already covered a couple concepts in 8.2, but I'm going to finish it off in just a minute. So check this out. So there they are. They got 2 sets. So R is a relation R and S are relations from A to B. Okay. So for all X and Y. Now remember, these are pairs, X and Y. So you're going to take one from A and one from B, and you're going to pair them up. And what this is saying to us. In other words, you're matching up. You're going to take one from here and one from here. By the way, it's easy because you're going to have 8 pairs. 4 in this one, 2 in this one. By the way, as we're doing probability, you'll note that it's probably coming across probability. You're like, geez, there's 4 choices here. There's 2 choices here. Geez, it's exactly the same as probability. And that's exactly right. So here they are. We want the X or Y. X or Y is defined such that the absolute value of X is equal to the absolute value of Y. Oh, cool. Right now, you can see the pairs. Negative 1, 1, 1, 1, 2, 2. Those are the ones that match up with that, correct? And XSY, X minus Y, is even. Okay? Well, let's think about that. So X minus, so negative 1 minus 1. Okay? Oh, just a minute. Geez, sorry about that. Got interrupted again. So x minus y is even, right? All right, cool. So if you match them up, -1 minus 1 is -2. That's an even number. Okay, remember that has to be divisible by 2. If you've forgotten, an odd number can be written in the format 2k plus 1, where k is an integer. Sometimes books use n, 2n plus 1, doesn't matter. An even number is just 2k. Okay, where again, k is an integer. So -1 minus 1 is -2. All right, cool. So -1, 1. And let's list them out here. So -1 minus 2, that does not work. 1 minus 1 is 0, so that works. 1 and 1. 1 minus 2 does not work. 2 minus 1 does not work. 2 minus 2 does work. 4 minus 1, 4 minus 2. All right, there they are. Okay. Now the question is simply this: which pairs are in A cross B? Okay, well, all the ones that we found. Oh, what are the pairs? So we need to list all the pairs that are in there. So the pairs that are in there are all 8 of them. Okay, I didn't match them up. Which ones are in R? These ones are in R. Which ones are in S? Cool. And then which ones are in A intersect S? In other words, which ones are in both sets? All right. Well, this one, and this one are in both sets. So they would be in the intersection of those two sets. That's where the overlap occurs. Okay. So specifically in 8.2, we talked a little bit about reflexivity, symmetry, and transitive properties, which is no big deal. We've seen that before. Think about this, what this would look like on a directed graph. Okay, if you had a relation where you had these numbers, it doesn't matter which ones you use. Well, you didn't have to be numbers even. They could be letters. Doesn't matter. If you saw this situation, okay, well, you wouldn't do it both ways. You do this. What do you know? Right off the bat, if those were in there, this thing is reflexive. Okay? How do I know that? Okay? I know that because B comes back onto itself. Okay? I know that C, D, and A. If this one is not here, it is no longer reflexive because it doesn't work for every member of the group. Okay? Now, if I drew this line in, okay, and I drew this line in, and I drew, I don't know, this line, and I don't know, just say this line here, for instance. It is not symmetric because the line, symmetric, yes, it's not symmetric because why? Because the lines don't go both ways. Does that make sense? In other words, for this to be symmetric, so I have right now, let's say oh, damn it. I'll call them back later. So let's say my relationship was E, okay? So right now we have the A, E, B, but right now the way the arrow is drawn, it's not B or E, A, which means it's not symmetric. Does that make sense? And so there'd be that. And so you're going to be looking at some graphs like this and seeing what's going on going forth, and we'll talk about it here, okay? We'll do a couple of examples of those real quick. Cool, here we go. So if you saw these was your set R2, let's say 0, 0, 0, 1, 1, 1, 1, 2, 2, 2, and 2, 3. Okay, so what I want to know is this. First of all, draw a directed graph. All right, cool. I can do this. 0, 1, 2, 3. So 0, 0. Whee! 1, 1. Awesome. 2, 2. Nice. Uh-oh. There's no 3, 3. So it's not reflexive. Okay? Based on that. So I got 0, 1. Notice I don't have 1, 0. So because I don't have that, it's not symmetric. Okay, from that one alone. Okay, I can finish drawing the rest of these in 1 to 2. Cool. and then 2 to 3. Nice. Okay, notice it doesn't have 3 to 0, though, so that's going to be an issue. Is there some hint of transitive property? Sure there is. 0 to 1, 1 to 2 is there, but it doesn't go all the way around. If it went all the way around, then it would be true. It's not transitive either. Okay? And there you go. Piece of cake. Okay? Yeah. So that's what you're going to be on the lookout for when you're doing some of those problems. Are they symmetric? Yes or no? Draw them out. Okay? Here's a fun one here. E is the congruence mod 5 for, no, not 5, mod 2. Mod 2 on Z. Now, if you've forgotten, Z is the integers. Okay? So for all M and N, for all M and N that are elements of Z, okay, M-E-N, should just use a big cappy so we don't get confused, N is equal to 2 divides M minus N. Okay? And that means that they are congruent. Okay, so what are we supposed to do here? We need to determine whether it's reflexive, symmetric, transitive, or none of them. Okay, well, let's find out. Okay, let's pick some integers. Cool. So if you take 6 and you take 2, those are our 2, right? What is 6 minus 2? Well, I don't know. Okay, 6 minus 2 is 4. Does 2 divide that? Sure does, right? It sure does. So 2 divided by 4, boom, there you go. 4 divided by 2 is 2, so yay. What does that mean? It means that these guys are congruent, mod 4, okay? Or mod 2, rather. And so you think about it, what that means is this. In mod 2 arithmetic, we're here and here, okay? We know they're both even numbers, so in essence, they're the same. So 2 means I just go around 1 time. 6 means I go around 3 times. Boom, but where do you end up? You end up with 0, the same thing. So when you take two numbers that are congruent in mod whatever, when you take the difference of them, they will divide, or the mod number, in this case 2, will divide their difference. That means they're congruent every time, okay? So in this case, there you go. You're like, what about two numbers that aren't? Like, so they could be two odd numbers, for instance. So 7 minus 1, for instance. Well, that's 6. Is 6 divisible by 2? It sure is. What does that mean? That this and this have the same mod number. In other words, in this case, both 1s, because they're both odds. We'll talk more about that with a different mod number here in a minute. So the question is it symmetric? That is, if you take 2 minus 6, the question is that congruent to 6 minus 2 in mod 2? And the answer is yes. It is. So what does that say to us? It says that it is symmetric. Okay. What about 7 and 7? Does 7 work for both these? Well, 7 minus 7 is 0. 0 divided by 2, it sure is. So yes, it's reflexive as well. Okay. So you pick a different number. You're like, okay, let's do 7, 3, and 1. Are 7 and 3 congruent? Well, 7 minus 3 is 4. 4 is divisible by 2, so yes. 3 and 1, the same. 3 minus 1 is 2. 2 is divisible by 2, so yes, they are. What does that say to me? It says that 7 and 1 are also congruent. And so there you go. So this is also transitive. Okay, this will be true for any mod number, but let's just try a different one. Let's just do, again, on the integers, but let's say it's for mod 6. Okay, so let's think about this for a minute. 9 and 15, for instance. Okay, well, what is 9 in mod 6? 9 is congruent to 3 mod 6. 15 is equal to divisible by 6 2 times the remainder of 3. So there you go, mod 6. Because they have the same value, they would be congruent. But look what happens. If you take 15 minus 9, what do you get? Well, you get 6. Is 6 divisible by 2? It sure is. What does that say about 15 and 9? It says that they are congruent mod 6. Okay, that's how you do that relationship. Okay. Cool. Here is another one. Nice. So this is number 22 on 8.2. And it's just another terminology piece that I want you to see. So let X equal the set of A, B, and C. And this, like, what the heck is it's the power set, baby. It's the power set. What does that mean? It means this. A, B, C, AB, AC, BC, ABC. And, wait for it, the empty set. That is the power set by definition of that guy. Again, there are 8 things that you can do with 3 terms, right? You could take all 3 of them. You could take none of them. You could take them 1 at a time. You could take them 2 at a time. And when you list that out, because for every single thing in that set, you have a choice. Do I take it or leave it? Okay? And so because it's binary, 2 to the 3rd power is 8 possible outcomes. There they are. I've listed them out for you. That is the power set. A relation n is defined on the power set. So n is defined on this by the following. For all A and B, so for all A and B in the power set. Okay. A and B is defined as the number of elements in A. The number of elements in A is not equal to the number of elements in B. Okay, and so we are to, in this situation here, okay, again, talk about whether it's reflexive or transitive or symmetric. Okay, that's all we need to find. Okay, you're like, wait, so seriously, like A and AB would be situations? Yeah, because there's 1 in this deal and there's 2 in here. What? That's it? Literally, that is all there is to it. Okay, so obviously B and AC and B and AB and so forth, so on and so forth. Okay, all of them with ABC. Okay, all of them with the null set. Any of the 1s go with the 2s and so forth. Would it matter if I did it this way? A, B, and then ABC, or ABC and AB? Would it matter? No, because they both work, right? They don't have the same number. So symmetric, yes. Reflexive, ooh, A and A. No, dude, they're the same. So that one doesn't work at all, right? That's reflexive, does not work. Transitive, I don't know, let's find out. So AB and A, right? AB, well, I'm sorry, A and ABC. Clearly that one works, right? Because then you got AB and ABC. True. However, well, I'll leave that alone. AB and A and AC. Ooh, that would suggest that this and this work, and this does not work. So transitive doesn't work. Symmetric does work. Reflexive does not work. Okay? Those are the sorts of things that you'll be doing in 8.1 and 8.2. Good luck. Let me know if you have any questions. Oops. Oh, fart. Stop.